Welcome to Dunwoody College of Technology, Mechanical Engineering. This is MENG2240, Mechanics and Materials. We're working through problem 813 this afternoon. In this problem we have a rigid cylinder. This is rigid. We're told here it's 24-inch diameter rigid cylinder. We're going to put around this hoop here. So this is going to be deformable hoop. And I believe this height is 1 inch, and the thickness is a 1/4 inch. I don't know if I can, it's pretty small, but we'll try to show it on here. And there we go. And its original diameter is 23.99 inches. So we're going to start out with 65. We're going to heat up this ring, slip it over the top, and then let it cool down to the same temperature again, back to 65. So we're looking for our pressure, the hoop stress, and that pressure that it exerts on the cylinder. So as we look at this, what do we have? We're going to try to figure out what our change in length is, and that's going to be pi times our diameter, right? So we need to go from 24 minus 23.99. That's how much we needed that ring to grow to slip over the top of that thing. So our change in thermal deformation is going to be equal to that delta L, and that's going to be equal to 23.99 pi, it's our original diameter, times T2 minus 65 degrees Fahrenheit, right? So that's our change in temperature, and times our coefficient of thermal expansion, which for, I believe this is A36, there it is, A36 steel. That, as we look it up, is 6.6 times 10 to the negative 6 inch per inch degree Fahrenheit. Alright, so how do we rearrange that? So we find that this is 0.01 pi equals that thing, so we're going to divide by 23.99 pi, and get rid of my equal sign there, and divide by 6.6 times 10 to the negative 6, and we're going to add to that 65 plus T2. Let's plug that in. T2 works out to be 128 degrees Fahrenheit. So we don't have to heat it up that much, but we need to heat it up about 60 degrees, give or take, to slide that over the top. So what force does that exert on our system, or pressure? So our force is going to be our AE delta alpha delta T. So our area here, we have 1 inch by 1/4 of an inch, and that's going to be, I'm going to put my delta here, times 10 to the negative 6. Temperature difference was 128 minus 65. E is 29 times 10 to the negative times 10 to the 6, and that should complete it, right? AE delta alpha. So we carry that through. We have something really small and something really big. It kind of works out to close to 1. So we find our total force here is 3,022.2 pounds force. Alright, so how does that get to a stress? Well, our stress is our force over an area. So we have 3,022.2, and that's going to be over 1 inch by 0.25 inches. So that works out to 12.09 KSI, about 12.1 KSI. So that's what our hoop stress on the ring. Maybe I shouldn't have said it quite as hoop stress, but that's just the internal stress on that ring due to being stretched. Sigma for the cylinder, going to be PR over T. So our force here was 12,088 psi. That's what this 1209 was. And we're going to multiply that by our radius, which was 12 inches. Divide that by our thickness, which is 0.25. P is 252 psi. There you have it. So we found our temperature, the stress on the cylinder, and the stress on the, so this was on the cylinder, this is the stress on the ring was there. So as you'd expect, the ring sees a lot more stress because it's smaller, and the cylinder is assumed to be rigid and has a lot lower stress as a result.